Here we're going to look at distillation of a binary mixture in a batch distillation where we have a total condenser, which means that the vapor, so this V is a molar flow rate of vapor, enters the condenser. This is where we're removing heat, so we form complete condensation to a liquid. Some of the liquid becomes the distillate, so this is a molar flow rate of distillate. The rest becomes a liquid flow rate that's returned to the column. So we have vapor flowing up, liquid flowing down, and then we have a still here where we start with some mole fraction of, and what we'll use the mole fraction, so I'm going to use X and Y, mole fractions of the more volatile component. And in particular, if I write X in and Y in, it means the mole fractions leaving that stage. So for the liquid, X3, X2, X1, Y3, Y2, Y1. So this would be Y0. The distillate mole fraction is XD. Well, that's the same mole fraction here. And YD has the same value as XD. So Y3 and YD are the same. The other term that we're going to use is the reflux ratio. So that's going to be the molar flow rate L, liquid, over the molar flow rate D, the amount the distillate that we collect. So V, of course, is L plus D, right? V is the flow rate coming into here, and we split it into two streams. So what we want to do is do a mass balance on this more volatile component, the one that we're using, X and Y. And let's do that. What I'm going to do is just pick a place that includes two of the stages. And I'm going to write a balance around that on this more volatile component. And so balance, how much flows in, better equal the amount that flows out. Well, in is Y1 times the vapor, the gas molar flow rate. And then out is X2 here. The liquid flow rate plus the other stream leaving is the D stream, XD times D. So I can write that. Let me rearrange it. So here's the rearranged version. And in general, I could write it this way. So this would be N plus 1. In other words, I could have picked to do the balance around the exit in stage 3, stage 1, and of course in a system we could have more than 3 stages. So this is a general form of that balance. Now we often write this in terms of this reflux ratio, and I'm just going to write the answer down. That L over V, if we just do the rearrangement, is R over R plus 1, and then D over V is 1 over R plus 1. And that's just by rearranging that we get this relationship. And it's just sometimes easier to work in terms of this reflux ratio. Well, this equation, or this one, same equation, is the operating line on an XY diagram where we want to determine the number of stages. So let's look at that diagram. So on the left, I've shown the complete diagram. This line then is this equation, the operating line. This curve is the equilibrium expression. For example, Raoult's law, something that relates the mole fraction of vapor phase to the mole fraction of liquid phase at equilibrium. And then what we're showing is how we step off the stages. So we can determine what's the distillate for this setup, what would be the distillate mole fraction that we collect. And what I've done is expand just part of that figure, but keep in mind that Y and X. And so for this particular example, the mole fraction in the still is 0.4 for the liquid. And if we then look at this value, 0.65 for the mole fraction of vapor, that's the vapor above the liquid that's in equilibrium. So that would be Y0. So if I now look at the point on the operating curve, this would be X1 and Y0. In other words, that's when I do a mass balance, those are the two terms that are going to show up in this equation, and that's why I've drawn this line. So this point is still X1, but it's Y1 because X1 and Y1 are in equilibrium. They're the mole fractions leaving. This is Y1. X1 and Y1 are in equilibrium, so they're on the equilibrium line. This point then would be X2 and Y1. The values here that we again, when we did a mass balance, substitute into this equation, so an operating line, and we continue this x2 and y2, they're in equilibrium, x3, y3. So this would be x of the distillate. And so for a batch distillation, keep in mind this is at an instant in time. As we carry out the distillation, we're changing the mole fraction in the still. So this point would move. This curve, which is related to this, would change as XD change, because XD changes as we change the composition in the still. But this hopefully gives you a better idea of why we count off stages the way we do in this batch distillation.